Bismillahirrahmanirrahim. Uh, Welcome to this recorded session by Bidirectional RNN, and it is the family of RNN. And this session is one of the part of Google ML Study Gem. And here I am Sajjadur Rahman. Once again, welcome to all you to the Bidirectional Recurrent Neural Network. So today's agenda: introduction, why BRNN, and we will also go through the vanishing and exploding gradient descent problem in the simple RNN, BRNN architecture and overview, and finally we'll show bidirectional RNN code on Google Colab. So let's start. Before I start with the bidirectional RNN, I give the overview of RNN and LSTM, which help you to understand what actually bidirectional RNN. Let's start. So sequences matter. Why sequence matter? Well, in right now, consider we have only three model or three machine learning model we have at ANN, CNN, and RNN. CNN is good for the image data. ANN is good for tabular data, 1D or sometimes 2D data, whatever you say, where the sequence is not matter. Like we see, if you have idea in the basic uh, data file processing or work, machine learning, prediction, diabetes prediction, weather prediction, forecasting, these things actually. So depend on actually whenever in terms some like audio or video, and also in the stock market data set where the sequences matter. For example, if you have an audio, if someone remove some clips in the middle and then you hear it, you will not get the full context because someone reduced some part. So this is the sequence matter. If you hear the full audio clip, then you know actually what the context it is. So there are other case in the stock market. Stock market, we see that the graphs are fluctuation over the time, and here the date is chronological order. That we you never, or I will not see, I would not see any graph which the orders are random, but it would be possible, I think. So uh, I think that you know that why the sequence is better now. And also basically we cover these details: LSTM, GRU, simple RNN, all of video you can find the recorded on my over the YouTube link, also YouTube playlist also. uh, but I just briefly discuss these things, that why need we LSTM over RNN. Well, when the first RNN, it has it shows that it has two problem, like vanishing gradient problem and exploding gradient descent problem. Don't worry. Vanishing gradient descent problem, what does it mean? By names we can predict that vanish means there's something that not exist. So during the back propagation, what actually we do, or what was our motive? Our motive is to reduce the weight, yet the model can adjust well and it can give better result. But in some cases we see that our actual weights are not reduced as what we expected. It's very negligible, almost to zero. That the times we call it the vanishing gradient problem. Exploding, on the other hand, like explosion, which means that large. So our goal is the reduce the weight and adjust it, but where we get actually more than the current weight. So definitely it cannot perfect fit, rather it can give the ambiguous result. So whenever we see this means that our model face the exploding gradient problem. So let's look at the LSTM. So LSTM comes from actually solve this issue. How it mitigate this problem? Well, it maintain actually two memory over the training time. One is long-term memory, another was short-term memory exists during the particular cell. And if you look at this the picture, you can see that this is the broad picture abstraction of a cell of LSTM, and inside it you can see that there is a hidden state, there is a cell state which long-term memory, this is short-term memory. And you can see there is the two type of activation function and some mathematical operation, so on so forth. And this is a good cell of LSTM. So here it refers STM, in some picture it's refer hidden memory, and this is long-term memory which represent the this memory, or it keeps the information which pass over the old cell. And you can see that where t minus 1, which means that the previous cell long memory input, and t minus 1 the just previous cell hidden output. And over the time we found the current time is the output. If we look at this, and this one is the current time input. So this is also the broad clear one picture. You can see that in the LSTM it actually divided into the three gate. First one is forget gate, and the input gate, which means the current time input, and the output gate. So don't worry, or if you want to more the mathematical equation, you can available a number of websites, or you can also check my the previous video too. Here our goal or part today's goal is bidirectional RNN. Why we need BRNN? As we have RNN, LSTM, GRU, and we know that the LSTM can solve the RNN problem. Why we need BRNN? Well, in some cases, like in the standard RNN, which works past to future, which means that it follow the chronological order, which means that we based on the current decision all in the previous one. But in the real world we need some make decision based on the future one. So do not compare like today how you will see the tomorrow what will happen, no. But we can predict or things, that things different. But in terms of the text, it is different meaning, you will see later, don't worry. Look at this example. Just I earlier said, first of all, if I read I like Amazon and I ask individually 10 person and they get randomly answer. If I ask that what does the Amazon refers, or what do you mean, or what do you understand after read this sentence or hear this sentence, I like Amazon. Someone say Amazon is river, someone say a website, someone say cloud company, someone say, you can say that a forest, river, whatever. They can say randomly, but I cannot deny their answer. I have to pick all of them answer because there is no clue we have, just limited this one. So if you look at the second sentence, I like Amazon order. So whenever I see this, the next word is order, Amazon order. The first thing come in my mind, not only mine but also anyone, that it is a website or commercial e-commerce. We can order anything here. This is a top class e-commerce site. How do we know this? We fix the thing based on the order. If there is no order, like instead of orders, if it has I like Amazon darkness, what does it mean? We can say predict this is forest. So what is the use case of sentiment analysis, name entity recognition, and the translation language. So just if you look this the previous example in the feed forward, how it over the time period, first I, then I like in the forward direction, I like Amazon, this one. But in the backward direction, what happened? So this is the backward direction things. If you just this is the simple give the idea how actually it works the forward and backward direction. So what are the advantages of bidirectional RNN? Well, it is comprehensive context, enhance the performance, better handling variable length, and improve the sequence level. So how you know that the performance, like over the time, it takes more time than it is less time for to predict the future than the vanilla RNN. So what are the disadvantages? Well, though bidirectional, which means at a time it gives to the forward and in the backward run. So definitely the computational time is high then compared to the others, longer training time and difficulty parallelization, risks of overfitting. So when does the overfitting or what does it means? In short, overfittings means it perform well in the training data. Whenever we give any unseen data, it gives the less predictable. For example, whenever we insert some input, it give me 70%, but whenever I put the training data, it give me the 99% accuracy. So before we go to the architecture of BRNN, you look at this two signal. So this one is the forward, this one is the backward. If you look at this, the broad one, so this one is our the vanilla RNN. We all know that over the here this is the input, but we also have the forward RNN. This one come, so together concate here, like this is RNN, this output is here, and over the time this RNN. So in the forward direction we just find for example I, but in the backward here, how do we get this? We need this output. How do we find this output? From here. How? Here in the last. So actually in fast cell we see the full sentence, just for simple understanding, full sentence, and here it is our the first word, here is the full sentence. Then this is our the first output of the forward RNN, and here is the we find this the B out, which means that the backward output, and finally we take the decision from this one. Basically if you understand this one, actually the similarly here. So over the time in the forward the input data goes longer and backward data considerable reduced, like just for example if we consider the length 1 2 3 4, so here the length is 4, here length is 3, this one is the discarded, but here the initially the forwarded length 1, but right now it has 2. So do not mess up with this, and the current both input take in the forward and backward RNN. So that's all about the theoretical. Now let's move into the coding part. Okay, this is the Google Colab. We know that Google Colab where we can easily run any machine learning, and it give us uh, the like how many well, here is also the Gemini. This is we can update or search anything here from here. If we get any confused, I just share this additional information with others. So we are connected my Google Colab, and you can see that it gives me 12 GB RAM, and this is the disk. So a limited one for example, whenever we run any image data or longer data, it takes require more than RNN. So this is the simple model, so we need not much enough memory. So I just run all it, and yeah, here we can see the running is start. If the complete it, we can see yes. Don't worry, I will share everything step by step what happened over the here. Okay, okay, the run is completed. But if you see how much, if you look at this, in the initial it was 1.2, after running this it has 1.6. If you want to change the run output like T4 GPU, it will be goes more faster. Okay, so I will run again after connecting one it, then I will share the others one, waiting for this. And look at this, I give also find the some GPU 15 GB. Okay, now I run this and change what will be the output. I know you already know this, then you can skip it. I share this those who have no idea. So if you look at this, in the initial it has 0.9, if I not wrong, or look at this clearly, but after complete the run it has 1.7, but 0.1 only very few GPU RAM use as the model time is less. So we use here TensorFlow, HDFI and Keras. So TensorFlow.keras dataset, don't worry, IBMDB is an a movie dataset. It is entire data, which means that it is a pre-trained dataset. So we can just search here IBM. Okay, IBMDB. So this one also we can go through the TensorFlow or Keras. Both are same but a little bit difference. So if you are beginner, then consider it is the approximately same. So this is the data set, and here it's tell how to load the data set actually. And if we visit this here, you can look like this. So we can download this toy data, and we need some sequence for RNN. We need to the padding sequence for like the length, maintaining their length. And we also import the embedding bidirectional LSTM dance dropout, all are from the keras layer. As modules we download sequential RNN and GRU model. So now go to the step by step. So IBM did load, and the number of word, how many word I have to download. I just want to download the 10,000. So I want to print the shape of this. So look like this, and if I print the white train, okay, I print similarly here, so you can get better understand. Yeah, this one also we can print split the test check here. And we just what the number of word here, we can also reduce this number, and we can the print the maximum padding length. And for the simple understanding we can just ignore it. So the first one is the simple RNN. So here is the simple RNN. We just call the embedding dimension 32. Over the whole model we fix it same, and the model we call sequential. So do you need to build any from the sketch? No, I don't think we do not focus building the model from the sketch. If you want to do more, then you can visit through this, but right now we just call it from the TensorFlow or Keras site. So visit this the Keras site here, just search on the Google Keras simple RNN, then you will find this site link. Here you can see that this is the some default value, and in the simple RNN, in the activation function is default 10h they use, and over the time you can see these all are the some values none, some are the false boolean. So whenever based on our tags and data set, we can change this like hyperparameter tuning, which one we can change true to false, false to true. Also we can change the activated function, and we will see then this the output. So if you also read this the documentation, which argument what does it means, and here you can see that clearly, which means that the default is none, but in the bias regularizer you can pass a bias vector. And how do you actually call this? There is then a simple code structure here actually. So this code simple RNN is not the different, is similar one. So if we visit also the TensorFlow, we can see these are the almost same. Okay, almost same. You can go through this documentation, you will get better understand. So if you want to know how actually define this minimal RNN cell, you can look at this the more complex code. So if I run this, then what will be the model summary? Simple RNN, here I pass simple RNN, and I just print the model, not train it with the data. I just want to see that how many trainable parameter. Almost all are trainable, non-trainable 0. Look at this the param, and here just follow this simple RNN and what I pass here. So here look at this the bidirectional RNN is like a same. Just search on the bidirectional RNN Keras and go through all the documentation. Whatever you need you have to change or you can do. And one thing I do not tell it earlier, that bidirectional RNN, it is not means we can apply it for LSTM, GRU, or simple RNN also. So by direction, it is not depend on the any particular like vanilla RNN or LSTM or whatever GRU. We can apply it for all. By direction, we can apply all direction in two part also. So here is that it's march model, how we march concate multi sum. Like if we remember in the, okay, go through back one here, and like this when we mark this model we can pass here actually what do you do, sum, addition, multiplication, or whatever we can choose from any of from this. And what we apply in our code we can see in the next one. So you can see that we pass bidirectional inside it simple RNN. So if you go to the bidirectional, by default it is concat merge mode. So if you want to change this we can change here in the default value, and uh, and here we can pass binary cross entropy, all are same as default. We just here we just want to see the change, any changing here. If we not run this model, so you cannot get the broad output here actually. So I just want to see that how we call it in the simple run and model parameter. But if we just one more way, okay, here the difference, can you notice that in the simple RNN 190, look at this, and what does it here, 380 bidirectional, which means that the first one 190 and as well as the second one similarly. Also here we pass bidirectional simple RNN, and then we pass the GRU inside the bidirectional. So what do you see? Is it change more than? So that's all about today's simple presentation of bidirectional RNN. Thank you for watching it.